So first of all, I didn't finish the tests. I'm almost done, but I'll get those done over the weekend and give them back to you on Monday.
How are they looking so far?
Great so far. Scores are a lot of perfect scores, a lot of near perfect scores. Okay, so I ended last time defining the compliance matrix, and before I did that, I talked about, so we know the stress tensor is this. And we can write that in Voigt form. Like this, just a column matrix of first the normal stresses, and then the shear stresses in this sort of backwards order. And we can define the state of strain. We only do that in the Voigt form. There's no mathematical benefit for us to writing it in a tensor in a matrix form. We're going to use this matrix form for the stress tensor. That's why we're going to use these two different forms. These will both be useful at different times. But the strain we're just always going to represent as normal strains, XX, YY, ZZ, and then the shear strains in that funny order, YZ, XZ, XY. And then the last thing I talked about was if, and these assumptions are important, if the material is linearly elastic and isotropic, okay, so let's first talk about what these mean. I talked about the linear relationship between stress and strain. I think I actually glossed over, I don't think I used the word elastic yet, or at least didn't define it. But this whole class is based on the idea of elasticity. So linearly means, mathematically, it's a linear relationship between stress and strain. So that's why the relationship is going to be a constant matrix. You have to go to more complicated math. Most simple finite elements, like the introduction to finite elements that I taught at for Twin Cities Engineering, that's also linearly elastic. So things get pretty complicated when the relationship gets nonlinear. Fortunately, most engineering materials in the range of loads that you use in engineering applications, there's a linear relationship. But so the short answer is most of the time when you're doing finite elements, you're still doing linear elastic. You're just doing more complicated geometry. Okay, so linear relationship between stress and strain. That's the linearly part. The elastic part. What does elastic mean? Who wants to tell me what elastic means? Elastic, you've used that word a million times. Yep.
Is it a material where if you deform it, it goes back to...
That's exactly right. Yep. So so the material deforms when it's under loads, and when the loads are removed, the material returns to its original shape. So it's not the fact that it can deform, it's the fact that when you remove the loads, it instantly is back to the shape it was in. That's what elastic is.
Could you say it has a memory?
Yes. So it returns to its original shape when the load is removed. What's it called? What's a material called? Anybody have a guess or happen to know this? When you load it, remove the load, and it stays deformed. That's true. But plastic. So when you talk about a metal going into its plastic region, or you talk about material plasticity, you're talking about something where you've deformed it past the point where it's, like materials will be elastic, like steel or something. It basically is elastic. Nothing's perfectly elastic, but it's basically elastic up to a certain point. When you cross that point, you bend it permanently and it won't go back anymore. Yep.
But when you cross that point and it becomes deformed, and you remove the loads and you put the loads back again, does it go back to elastic again?
Yep, it does, but it has a new resting shape. And then what does isotropic mean? This is like the only thing you have to learn this whole semester is the difference between homogeneous and isotropic.
Same in every direction?
Every direction, yeah. Okay, that's not the only thing, but that's an important thing. Same behavior in every direction. If that's the case, then the Voigt strain is equal to this 6 by 6 matrix. I'm going to write out all the elements here. So 1 over E, negative nu over E, negative nu over E, 0, 0, 0. I'm tricking you into writing this down multiple times. It's a teaching trick I learned. Negative nu over E, 1 over E, negative nu over E, 0, 0, 0. They make you take these teaching classes before you get your your permanent job. They can't enforce that you use the stuff that they say, but they make you take the classes. Third row is negative nu over E, negative nu over E, 1 over E, 0, 0, 0. Fourth row, 0, 0, 0. And then in the fourth column, 2 times the quantity 1 plus nu over E, then 0, 0. And now this term just moves 1 to the right with every new row. So now it's the fifth column, 2 times 1 plus nu over E. Is this one of those times when I'm going fast? Yes, it is, sir. Isn't it? Yeah. See, I could tell there. And then the sixth row, same thing, but this is just in the sixth column. And all of this is multiplied by the Voigt stress. This matrix is called the compliance matrix. And so would a really flimsy material have big values for the compliance matrix elements or small values? 50% chance. It's It's called the compliance matrix because if it's very compliant, the numbers are big. You know, you can think of it that way. It's this is a measure of how compliant it is.
Can you say that again?
Yeah, the more compliant it is, the bigger the values of the compliance matrix are. Like you can think of each of these measures as, each of these elements as some kind of measure of how easy it is to deform the material. So you get bigger values if it's easier to deform. Engineering materials are the stress values we're going to be dealing with are going to be really big. The strain values are going to be really small. So these elements are all going to be tiny, you know, something times 10 to the negative 9, negative 10, negative 11, that kind of stuff. Okay. And all of these, this compliance matrix depends on two values. Two parameters. E, the Young's modulus, or the elastic modulus, or the stiffness. And the Young's modulus is a measure of if you put something into tension, how much it stretches in that direction. And since all of this works for positive or negative values, it's equally a measure of if you put something in a compression with a certain amount of load, how much is it going to squish? So let's say how much stretch you get for a given axial tension.
Can you treat when you put the material through the acoustic test, vibrations,
Mm-hmm.
can you treat it as if you're, at every instant, you're putting some sort of load on it, and then it goes back to its original?
An acoustic test?
Yeah, basically the vibrations. You know, if you're launching something on, like, say a rocket, before they launch it, they put it through acoustic test, which basically they introduce different types of vibrations to the material or the assembly.
I don't know.
You don't know?
Yeah, we can talk about it later and maybe we can figure it out, but I don't know anything about that. And then the second parameter that it depends on is the Greek letter nu. That's called Poisson's ratio. And that's a measure of how much the sides contract when you put something in tension. When you put into axial tension. So, for example, if you take this material and you apply a force this way, the deformed shape is going to, this is exaggerated, but it's going to look something like this. So the tension is going to make it get longer in the direction of the axial force, but there's going to be a corresponding contraction in the other direction, and it's not going to preserve volume. That might be your first thought. In some materials it will, but in most it won't. But it'll contract in like this if you put it in tension, and if you put it in compression, turn those forces around, it'll bulge out in the sides. And so that's what the Poisson's ratio tells you. This is called the Poisson's effect. So a material that has a big Poisson's effect, a big Poisson's ratio, is one where you apply an axial load and you get a big change in the thickness in the perpendicular direction. And actually, cork, if you measure its Poisson's ratio, it's almost 0. That's unusual, but cork isn't really like an engineering material. But when you think about it, it makes sense that that has become the material that you use in wine bottles, because when you pound something into a glass wine bottle, you're putting a axial compression on it. Most engineering materials, if you try doing that with metal, every time you hit it with a hammer this way, it would bulge out this way, which would break the glass. And so that's why cork is a useful material for that. Okay. So, for example, say that you have a stress element that looks like this. Let's say that we have an axial tension in the x direction of 5 times 10 to the 7th pascals. And then the xy shear stress is 1 times 10 to the 7th pascals. And the xz shear stress is in the negative direction with a value of 2 times 10 to the 7. In order for this to be in equilibrium, that means you also need one going this way that matches that 1 times 10 to the 7. And you also need one this way matching the 2 times 10 to the 7. And let's say that we've done material testing on this material that tells us that the Young's modulus is equal to 200 times 10 to the 9th pascals. And the Poisson's ratio is equal to 0.3. Say we want to know what the strain is for this material. Well, the Voigt strain then is just equal to the compliance matrix using these two values times the Voigt form of this stress. So that's the compliance matrix times the Voigt stress looks like this, 5 times 10 to the 7th in the xx direction, 0 yy, 0 zz, 0 yz shear stress, negative 2 times 10 to the 7 xz shear stress, and 1 times 10 to the 7 xy shear stress. And if you plug that into your calculator, you get values of 2.5 times 10 to the minus 4, negative 7.5 times 10 to the minus 4. This one is negative 7.5 times 10 to the minus 5. Then another 7.5 negative times 10 to the minus 5. Then 0. Then negative 2.6 times 10 to the minus 4. And positive 1.3 times 10 to the minus 4. Okay, and based on this, you could draw pictures of what the, you could draw a little representation of what kind of deformations are happening. We know it's getting longer in the x direction. We know it's getting shorter in the y and z directions, we know that the angles between the positive y and z faces are staying the same. The angle between the positive x and z faces are becoming more obtuse, and the angles between the positive x and y faces are becoming more acute, just by the definitions of what the strains mean.
This is unitless, right?
What?
This is unitless?
The strain is unitless, yep. And Poisson's ratio is unitless too. Okay, so the next question is, yes?
What is C again?
That's the compliance matrix. That's this.
So can you also say then that the x direction is in tension, the y direction, the z direction are in compression? Can you think of it that way too?
I would use the stress to think about it that way, and I would use the strain to think about how the shape changes.
Okay.
So yeah, from the stress tensor that I gave, like you can look at this and just see it's being, we know that the x direction's in tension because there's a force that way. The negative face that's obscured is equal and opposite, so it's pulling that way. And that's how you know what the loads are doing. And by the way, these numbers represent steel, and there's different kinds of steel. They all have about the same Young's modulus, and there's some differences in the Poisson's ratio. They vary a little bit between 0.25 and 0.3 or something.
Question for you.
Yes?
When you're talking about the Poisson's effect,
Mm-hmm.
when you look at the picture at the red, should it be more like a curve?
Well, it depends what that loading pattern is. If this
Linear, then it's going to be just, stretched out. And
if this is a distributed load, it looks like this. If it's a point force, that's kind of beyond the scope of what we can talk about. But that brings up something that's going to be important in this class that I haven't talked about yet, but we'll talk about pretty soon, and that is there's a difference. I don't want to put this on here yet, but there's a difference between something loaded like this, for example, and something loaded like this. They're going to deform differently, and their stresses are going to be different. This one is going to deform into a shape like this, and this one is going to do something more like what you're imagining, where there's going to be big local deformations close to those point loads, and then there's going to be weird stresses in here. But what we are going to see is that, I shouldn't have drawn it that much different, because this is what I'm trying to say. Is that if you cut off some small amount at the ends, if you just admit that we don't know what's going on here or here, all the stresses and strains in this region match all the stresses and strains in that same region here. And so we're going to, when we have complicated loading patterns like this, we're going to assume an easier uniform loading pattern, and then we're just going to throw out our results at the end. We don't know what's happening right near the loads. So that's going to be an important thing, and I'll talk about it in more detail going on. So yeah, I think it's probably the case that a lot of times, if I'm not thinking about it, I'll draw something as if there's a point load, when what I really mean is we're going to treat it like there's a distributed load acting over that whole face. So really what I'm talking about here is a uniform distributed load acting there and there. Okay, so I said that this is Young's modulus and Poisson's ratio for steel. How do you come up with those? So that's the next question. How do you figure out Young's modulus and Poisson's ratio for a material? Well, you do it with a tension test or a tensile test.
So you got to do it experimentally?
Yeah, right. I mean, unless you don't have to do it experimentally anymore for some specific kind of steel because someone's already done it.
Right.
But yes, you have to do it experimentally. So you take a sample piece like this, and you clamp the two ends. And you make two marks on the material and apply forces here and here. And then Young's modulus, you apply that force and then you measure, what's going to happen is this stretches out here, this stretches out here. The material gets a little longer and a little thinner. And so let me call the x-axis the up-down axis. That's the loading axis. And the y-axis is that perpendicular axis that you can see in this picture. Then the Young's modulus is equal to the stress in the x direction, the normal stress in the x direction, divided by the normal strain in the x direction. And the Poisson's ratio is the negative off-axis strain. So in this case, that would be the YY strain divided by the axial strain, EXX. So you apply that load, you get it to stretch, you measure the change in that distance and use that to measure an axial strain. You measure this distance and use that to measure the off-axis strain. And then you use your measurements to calculate those values using these definitions. Okay, so let me give you some fake data and we'll calculate this. So example. So let's say that we have a rectangular solid before deformation. This thickness is 1 centimeter, 0.01 meters. The width into the page is 2 centimeters, so 0.02 meters. And the height is 10 centimeters, 0.1. And let's say that we, so now we put this object into 5,000 newtons of tension. And when we do that, let me put some axis directions on here. So let's call this the x-axis, this the y-axis, and then the z-axis is coming out. 1, 2, yeah. So we're applying this tension along the x-axis. Yeah, we're usually going to use, it won't really matter yet, but later on we're always going to put the x-axis along the direction of tension. Okay, so when the load is applied, we get a change in length along the x-axis of, let's see, of 3.0 times 10 to the minus 5 meters. And we get a change in, actually, sorry, I know you hate when I do this. Let me just report what the measured lengths are, and then we'll go from that into the calculation. So the length along the x-axis is 0.10003 meters. The length measured along the y-axis is 0.0099931 meters. And we want to know what Young's modulus and Poisson's ratio are. Okay, well, the definition of Young's modulus is the axial stress divided by the axial strain. These are normal stress and normal strain. So this is going to be sigma xx divided by EXX, epsilon XX. Sigma XX is equal to 5,000 divided by the area of the loaded face. So if we have a force acting like this, that area is going to be 0.01 times 0.02. And so that's 2.5 times 10 to the 7th pascals. This is newtons. These are both meters. Epsilon XX is equal to the deformed length, which is 0.10003 minus the resting length, divided by the resting length. And so here we get a value of positive 0.0003. And so Young's modulus is 2.5 times 10 to the 7 pascals divided by 0.0003 unitless, and we get a value of 8.3 times 10 to the 10th pascals, or 83 gigapascals. And then for Poisson's ratio, we already have the axial normal strain. The formula that we're going to use, the definition, is negative epsilon yy divided by epsilon xx. So we need to calculate epsilon yy. So that's equal to the deformed length in the y direction, which is 0.009931, minus the undeformed length in that direction, divided by the undeformed length, and we get a value of negative point. Shoot, I shouldn't have used this example. These numbers don't work. Well, they'll give us values. They're just not realistic values. Let's see. How do I get back there? Okay. Okay, so if you do this calculation, you get epsilon yy that's equal to negative 0.00069. And so Poisson's ratio is negative of that negative EYY strain, so negative 0.00069 divided by the XX strain, which is positive 0.0003. And so you get a Poisson's ratio of 2.3. That's how you do the calculation. Okay, so think about that for a second, and then I'll tell you why that number doesn't make any sense. Anybody have any questions about that calculation? Okay, so Poisson's ratio values can only range between 0 and positive 0.5. So 0 to 0.5. A material that has a Poisson's ratio of 0.5 is a material that maintains the same volume through every deformation. So 0.5 means a material it's called incompressible. That doesn't mean you can't change its shape. It just means that its volume stays the same under deformation. So anything bigger with a Poisson's ratio bigger than 0.5 means that you have a material where if you press on it or pull on it, the net effect is making the volume increase, which makes no physical sense. By the way, most engineering materials have Poisson's ratios pretty close to 0.3. So if you ever don't, the Young's modulus varies a lot from material to material. Poisson's ratio, if you ever don't have a measurement for that, 0.3 is a reasonable guess. You won't go too far off by assuming an engineering material has a Poisson's ratio of 0.3. Okay, so now we know everything we need to know about the relationship between stress and strain. That means that if you have a way to calculate the stress for a material in a given loading environment, all you have to do is multiply that matrix to the stress, and it'll give you the strain. It'll tell you what the deformation is. And that's just sort of the end of the story with the relationship between those two things. The next thing that we have to talk about is re-expressing stress tensors in new coordinate systems. This is called stress transformations. And this is going to come up pretty often. So often we'll want to re-express a stress tensor in a new coordinate system. The main reason that we're going to want to do that is here's the main motivation for that. For any state of stress, there is a coordinate system where, so you load a material, whatever forces are applied to it, and you choose a point in the material, and you calculate the stress at that point. Okay? No matter what the loading is and what the material is and whatever, for that point, there is a coordinate system, some orientation of the coordinate system, where every stress, every non-zero stress is a normal stress, where all the shear stresses are gone. And that's a little surprising. I mean, it is surprising. And even better, when you find that orientation, one of those, so now you have three normal stresses, or your only non-zero stresses. One of those is the greatest value of tension that's possible at that point for that loading, and one is the greatest amount of compression that's possible for that loading. And based on those two values, the third thing is you can find the coordinate system where you have a shear stress that's the greatest possible shear stress you can have for that loading. So by re-expressing a stress tensor in new coordinate systems, you can figure out the greatest tensile load happening at a point, the greatest compressive load happening at a point, and the greatest shear load happening at that point. And those three things are hugely important for figuring out when a material is going to break. And so that's the motivation is we're going to find coordinate systems where, so we're going to find coordinate systems where the point is in maximum tensile stress, compressive stress, and shear stress. And those are very valuable for predicting fracture. Or any kind of damage. Okay, so before we can find those particular coordinate systems, we need to figure out mathematically just how to change arbitrarily from one coordinate system to another one. And the way we're going to do it is related to the way that you do it with vectors. So if you have a vector, a vector pointing that direction, and you know what the components are in this coordinate system, what do you need to do to re-express that vector in this coordinate system? What's the tool you use? Yeah, you multiply by a rotation matrix. And we're going to do the same thing with tensors. We're going to use it a little bit differently. So just like with vectors, we'll use rotation matrices to re-express the stress tensor in the new coordinate system. Okay, so in statics, the rotation matrices I talked about were all two-dimensional. They were 2x2 matrices. Now we're going to be doing all this stuff in 3 dimensions. The ideas are the same, but there's a little more you have to worry about. So okay, let's define this rotation matrix Q. So let's say that vector v relative to, so let's say there's a coordinate system A and a coordinate system B, okay? And say that we know the components of a vector v expressed in A, in coordinate system A, okay? Then define a matrix Q whose columns are the coordinate axes of A expressed in coordinate system B. Then vector V expressed in coordinate system B is going to be equal to that rotation matrix times vector V expressed in coordinate system A. This is the one that you knew beforehand. And this is the transformation that you wanted to make. Okay, so the key thing is, if you're going from A to B, that rotation matrix, the columns of that rotation matrix have to be the coordinate axes of A expressed in B. Let me show you an example, that's sort of an intuitive example of this. So let's say that we have a vector with a magnitude of 10 that makes an angle of 30 degrees with the horizontal. And in a coordinate system like this, that vector is equal to 10 times cosine of 30, 10 times sine of 30, so that's 8.66, 5.0. What are the components of this vector? In a coordinate system oriented like this, where that's the x-axis, that's the y-axis, and this angle's 30 degrees. Okay, so look at that for a second. I didn't draw it super clearly, but this angle is the same as that angle. So can you look at that and tell me what the components of that vector are going to be? So we're not going to move the vector at all. All we're doing is re-expressing it in this new coordinate system. It's just going to be, so now what we're going to have is a vector with a length of 10 that's pointing just totally along the x-axis. So the components are just going to be 10, 0. You see that? So we expect this vector to have components 10, 0. So now let's think about that definition of the rotation matrix, and hopefully we'll get that answer out. That's what it needs to be. Anybody have any questions about, or want to look at this a little longer or anything to figure out why this is going to be? So it makes sense what these components are in this coordinate system, right? Anyone having trouble seeing why in this rotated coordinate system that should be 10, 0? Yep. Okay. So here's the original coordinate system. Now the rotated coordinate system is this. And so if you just think of the vector components, just say, for this vector, how far do you have to go along the x-axis and how far? So this has a length of 10. We're just going to go 10 along the x-axis. Okay, so if we call this coordinate system A and well, I'll do that in green. Call this one A and this one B. The rules for that rotation matrix say the columns of this rotation matrix have to be the axes of this coordinate system as expressed in this coordinate system. So the x-axis is the x-axis of the A coordinate system is pointing that way, right? We have to say what the components of that are in this coordinate system. And then the y-axis of A is up. We have to give the components of that vector in this coordinate system. And then the z-axis, they're both the same because it's rotating around the z-axis. Okay, so the x-axis of A expressed in B. So let me draw. The x-axis is like this. There's the B coordinate system. This angle is 30 degrees. And so we have to give components for this green vector in this red coordinate system. You can think of that as it has a length of 1 because it's a coordinate system axis. So it's going to be 1 times the cosine of negative 30 degrees, sine of negative 30 degrees. So it's going to be 0.866. No. .866, negative 0.5, and then it's not, I shouldn't leave off the z-axis, we're going to need that. So that green arrow doesn't have any component in the z direction. So you get 0.866, negative 0.50.
Why do you have a 1 in front of the...
Because this green vector is a coordinate system axis, and so it's a unit vector. So that's the length of that vector. And then this, the cosine and sine just give the direction. Okay, so there's the x-axis. Now we have to do the y-axis. So the y-axis of the A coordinate system expressed in the B coordinate system. The y-axis of A is vertical. There's the B coordinate system. And this angle is 30 degrees. Bless you. Okay, so that green vector in this coordinate system, from the positive x-axis, you have to go positive 60 degrees to get to that vector. So you're going to have, you have a unit vector length of 1 times cosine of 60, sine of 60, 0. and that's equal to 0.5, 0.866, 0. And then the last one is the z-axis of A expressed in B. That one doesn't change. They both have the same z-axis, so this is just going to be 0, 0, 1. And now these three vectors that we came up with, these three sets of components, are the columns of our rotation matrix. So now this rotation matrix Q is equal, the first column is equal to 0.866, negative 0.50. The second column is equal to 0.5, 0.8660. And the third column is 0, 0, 1. And so our vector components in the B coordinate system are equal to this Q matrix, 0.866, negative 0.5, 0, 0.5, positive 0.866, 0, 0, 0, 1, times that vector v expressed in the A coordinate system, which is what we started with. That was equal to 0.866, 0.50. Yes, thank you. Yep, you're right. Yeah, so this should be 8.66, 5.00. So the idea is the original vector is this. That's the original vector in the A coordinate system. We knew by thinking about it that when we did this transformation, we should get vector components out that are 10, 0 or 10, 0, 0. Now we're doing the transformation and checking to make sure that that happens. And it does. So that's what it had to be. Any questions about that right now? Okay, so that is a general definition of the rotation matrix. You'll be happy to know that we're not going to have to use that definition. We'll have a simpler way to do it. But this way always works. The other way that I'm going to give you, it's always going to work in this class, but it's not quite as general. But so let's take a 10-minute break. Come back at 2:15, and I'll go into the practical way that we're going to calculate these rotation matrices. And then I'll talk about how to use them with stress tensors. All right, so that way of thinking about rotation matrices, so the columns of the rotation matrix are the A coordinate axes expressed in the B frame. It's a tedious way of doing it. So I'm going to give you these three definitions of rotation matrices. One if you're rotating the coordinate system about the x-axis, one if you're doing it about the y-axis, and one if you're doing it about the z-axis, and then it's just always the same in those cases. So first, So if you want to rotate a coordinate system theta about, and so now I'm going to do it about all the three different axes. And when I say about, I'm talking about according to the right-hand rule. Okay, so first for the x-axis, the rotation matrix is 1, 0, 0, 0 cosine theta, sine theta, 0 negative sine theta, cosine theta. If you're going to rotate it about the y-axis, it's cosine theta, 0, negative sine theta, 0, 1, 0, positive sine theta, 0, cosine theta. And third, about the z-axis, Q is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. And notice that the form looks pretty similar for all of them. You have whatever axis you're rotating about, that entire row and column are zeros except for that axis. Okay? And then in the other ones, you have a cosine, a sine, and a cosine. It's the same order of things for the x and z rotation matrices. The negative is in the opposite place for the when you rotate about y, and that's because in everything y just has to be a little bit different. The y-axis always has to throw a little wrench into your plans. It's just its way. Okay, so let's do that same example we just did, thinking about it this way. We know that in this coordinate system, this has a length of 10, and this angle is 30 degrees, and the vector is equal to 8.66, 5.0, 0. What are the components in the rotated coordinate system? Where this angle is 30 degrees. Okay, well, what you have to do is figure out what kind of rotation you're doing to get from the original coordinate system to this coordinate system. You know, we're going from this to this. In both cases, the z-axis is pointing straight at us. So what kind of rotation is that according to the right-hand rule? Is that a positive or a negative rotation, and what axis is it about? positive about z. Yep. So so theta is equal to plus 30 degrees about the z-axis. Any questions about that? How you see? Anyone not seeing that yet? So you're rotating it this way, counterclockwise in that plane. The axis is your thumb for it to be counterclockwise, and your thumb is in the same direction as the z-axis, so that's a positive angle of 30 degrees. If we were going from this one back to this one, it would be the opposite. You'd be rotating like this. Your thumb is in the negative z direction, so it would be a negative angle. Okay, so that means that the rotation matrix is equal to cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. And that's the same thing we got before, 0.866, negative 0.5. I'm reading off the columns here for some reason. Second column is 0.5, positive 0.866, 0, and then 0, 0, 1. And so now the vector expressed in that new coordinate system is equal to that matrix we just got, 0.866, negative 0.5, 0, positive 0.5, positive 0.866, 0, 0, 0, 1, times our original matrix, our original vector in the original coordinate system. So that was 0.866, 0.5, 0. And if you multiply that out, you get 10, 0, 0. Yes, I did that again. 8.66, 5.0, 0. Yep. Any questions about that? Okay, so yes.
Will we be provided those three matrices for the X, Y, and Z?
Yes, but what you should do is program it into whatever you're using. Put it in your calculator, or if you want to use MATLAB on a laptop, or that's fine too. But you'll be a lot happier if you have a program where the one that's listed on D2L, it's like you just enter in the angle and you enter in the axis number, and it produces that matrix for you, so it's really fast. Okay, so to re-express a vector in a new coordinate system, you just left multiply the vector by the matrix, right? It's similar to re-express a tensor in a new coordinate system. The tensor in the new coordinate system, or maybe I should use that same notation I was using. So the tensor in the B coordinate system is equal to the rotation matrix times the tensor in the A coordinate system times the rotation matrix again transpose. So you need 2 of these rotation matrices instead of 1 like the vector. And the way you can think about that is one rotation matrix has to do with re-expressing or transforming the faces of that stress element. And the other rotation matrix has to do with re-expressing the tractions on those new faces. So when you're transforming a vector, all you're doing is re-expressing a vector. With a stress tensor, you're re-expressing faces, and then you're re-expressing vectors on each of those faces. You know, those traction vectors are vectors, so that's why you have 2 in this case, and you only had 1 before. All right, so let's do an example with a stress tensor. So let's say that we have So let's say this is our stress element. We have the XX stress is positive 5. The XY stress is 1. Oh no. Let's see. Okay, XY stress is positive 1. The XZ stress is positive 2. And then we get matching ones for each of those. On the Y face, we have a Z component of the traction of negative 10, so that's 10 going back towards the back. And that means we have to have, on the front face, 10 down towards the bottom. And then the last thing is, on the Z face, we have a normal stress of positive 3. Okay, so first, what's the stress tensor in a coordinate system like this, like we're used to? And then second, what's the stress tensor in a coordinate system with the z-axis this way, the y-axis up, and now the x-axis has to be going back into the page. Okay, so for part A, this stress tensor is 5, 1, 2. Then 1, 0, negative 10. Then 2, negative 10, positive 3. All right, so now that we have this, and these are all in megapascals, we want to use the stress tensor that we got for part A to represent the same state of stress in the new coordinate system. So what kind of rotation do you have to do of that original coordinate system to end up in this new coordinate system? That's right, 90 degrees positive about y. So you have to rotate like this to get the z-axis to go over there and the x-axis to go back. Okay, so that's plus 90 about the y-axis. So theta equals plus 90 degrees about y. So the rotation matrix is cosine of 90, 0, negative sine of 90, then 0, 1, 0, then sine of 90, 0, cosine of 90, so that's 0, 0, 1, 0, 1, 0, negative 1, 0, 1. And so the stress tensor in the new coordinate system is equal to that Q times the old stress tensor that we already calculated, that's 5, 1, 2, 1, 0, negative 10, 2, negative 10, positive 3, times the transpose of Q. So doing the rows, that's 0, 0, 1, 0, 1, 0, negative 1, 0, 1. And you don't want to, you want to program this into your calculator because you don't want to do that by hand. It's a nuisance, but it's instant on your calculator. And you get 3, 10, negative 2, 10, 0, 1, negative 2, 1, 5. In this case, because this coordinate system is at right angles to our old coordinate system, we can actually check this and make sure that it makes sense, because we can draw a stress element with our new coordinate system. So we have y up, z that way, and x that way. It's a little bit of a nuisance to do this because now we see that this is the negative x face that's pointing towards us. So we have to, we're going to have to use the negative values when we draw on this. But what we're going to see is if we do this right, when we draw all these values on the stress element, we're going to get the identical stress element we started with. Okay. So on the z face, we have 5 is the normal stress. In the positive y direction, we have 1. In the negative x, in the positive x direction, we have negative 2. So in the negative x direction, we have 2. That means that has to match, and that has to match. Now on the positive y face, we have no normal stress. In the positive x direction, we have 10. That's towards the back. And so that has a matching stress on the negative z face. And then we already drew that 1 in. And now on the x face, on the positive x face, we have 3, 10, negative 2. On the negative x face, we have negative 3, negative 10, positive 2 for equilibrium. So these two are already drawn. The 2 and the 10 are already drawn. We just have to draw the the 3 is in the negative x direction, which is this way. And hopefully that's identical to, I think it is. Any questions about that? Okay, so let's see what happens when you have a stress tensor so we saw that if you do rotate the coordinate system at right angles to your old coordinate system, it's pretty easy to interpret the results, make sure it makes sense. That's not the case when you rotate at other angles, but let's just see what happens. Let's do one like that. So here's another example. So let's say that in this coordinate system, this standard coordinate system with x to the left, y up, z out of the page, the stress tensor is 0, 0, negative 2, 0, negative 50, positive 10, negative 2, positive 10, negative 20. That's all in megapascals. And the question is, what's the stress tensor in a coordinate system rotated plus 30 degrees about the z-axis? So we're talking about a coordinate system where the z-axis is still in the same direction. The x-axis is that way, and the y-axis is this way. Well, this new stress tensor is going to be equal to, we're going to have cosine of 30, sine of 30, 0, negative sine 30, cosine 30, 0, 0, 0, 1. Then our original stress tensor, 0, 0, negative 2, 0, negative 50, 10, negative 2, 10, negative 20. And then the transpose of this matrix, which is cosine of 30, negative sine of 30, 0, positive sine of 30, cosine of 30, 0, 0, 0, 1. And if you multiply that all out, you get this new stress tensor of negative 12.5, negative 21.65, 6.732, negative 21.65, negative 37.50, 7.66, 6.732, 7.66, negative 20. And those are all in megapascals. So you can see in the original one we had this really big normal stress in the y direction. Now some of that has become shear stresses, some has become normal stresses in other directions. It's sort of hard to visualize what's going on, but you can still draw out the stress element and figure out, that stress tensor corresponds to a stress element just the same way the other ones do. I'm going to draw the stress element in the usual orientation, but now we have 12.5 going into the x face. On the x face we have 21.65 acting down. On the x face we have 6.732 in the z direction. On the y face we have 37.50 going into the face. 21.65 to the left, and then 7.66 in the z direction. Then we have 6.732 to the right, and a force into the z face, stress of 20. Okay, so we get this sort of unpredictable connection between shear stresses and normal stresses in one coordinate system to new shear stresses and normal stresses in another. But of course, somewhere there's a coordinate system where the shear stresses are the biggest they can be, you know. Somewhere there's a coordinate system where the normal stress is as positive as it can be. Somewhere there's an axis where the normal stress is as negative as it can be. And those are the values that we're going to be trying to find. And that's what we're going to use this eigenvalue problem for, to calculate the principal stresses. Any questions about that? Okay. I think there are a lot of problems. I'll give you some problems for the weekend where you just have to calculate these rotation matrices, do this stuff, redraw out the stress element, and you'll get used to it. Okay, that's it.